It's wonderful to link what you are studying on papers with your real life. In particular, the internal forces of a beam like bending moment and shear force. Look, whenever you apply a force on a beam and the reaction force that reflects your force is not that strong, the beam will absolutely be broken, right? And once it broke, there will be always three things you have to keep them in mind, which are shear force, bending moment, and normal force. Regardless of the normal force, because it depends on the reaction force that acts horizontally with the beam, the shear force and the bending moment have maximum numbers. And it's so important to know where exactly is the shear force and the maximum bending moment in order to put specific materials to strengthen these weak parts, avoiding any failure. Now we will have some examples to elaborate the idea of internal forces, also to draw the shear force and bending moment diagram in order to determine where is the maximum shear force and the maximum bending moment. Let's go.
Hi guys, in this video we are going to draw the bending and shear force diagram. Now we have a beam. Now we are going to find the bending moment and shear force 3 meters away from A. It seems to be here. So we have 2 meters here and 2 meters divided by 2 here. So we have to cut here. Okay, we get something like this. We have normal force and shear force and bending moment here in point 0. Okay, so to calculate this bending moment, I assume it this direction. M0 equal 0. So MO minus 2 multiplied by 3 the distance plus 2 multiplied by 1 equals 0. MO equal 4 kilonewton meter. So the summation force in y direction equals 0. The summation force in y direction will get us the V. To find the shear force, so summation force in y direction equal 2 up minus 2 down minus V down equals 0. So V equals 0. Why V equals 0? We will see. Now we are going to draw shear force and bending moment diagram. It's quite easy. So we will start from this point 0 and we will go up 2 because this force, and nothing here. We'll go down 2 because this force, and nothing here, and go down 2 because this force, and nothing here, and finally go up 2 for this force, and we reach to 0. So now we have draw shear force, and now it's to bending moment. We will go up 4 because this area, and you go up 4 and nothing here because don't have any area here, and go down 4 because this area, and we reach 0. And now let's go to solve a more complicated problem with my friend Musa.
Hello everyone, in this video we are going to draw the shear force and bending moment diagram in order to see the maximum shear force and the maximum bending moment. Okay, we got a beam and there is two forces acting on it, 15 kilonewton and 24 kilonewton, and it was actually distributed load, and we converted into one single load and we got our reaction forces. And before we start, I want you to know the integration of this line is just the slope, something like this, and the integration of this is a curve, and the integration of the curve is more curved. Anyway, okay, let's get started. So we got a 21, so we move up 21 corresponding to this force, and then nothing here, just travel, and then move down 15. So 21 minus 15 is 6, actually it's 6, and nothing here. And here, because this is a straight line, so the integration is going to be slope, so we move down 24. So 6 minus 24, 6 minus 24 is basically minus 18. Okay, here is minus 18, so nothing here. And then actually we move up 18, bam, we reach to 0. Okay, and now before we draw the bending moment diagram, it's important to calculate the areas. Okay, so the area of the rectangular here is very easy. 21 times 2 base times the height. 21 times 2 is going to be 42 positive, and here 6 times 2, 12 positive. And now the area of the triangle is actually the base times the height divided by 2, but the problem here is we don't know the base. Okay, say let's call it x, and the height is 6. Okay, in order to find the 6, first of all, we know that the shear force here at this point is actually 0, right? So we can solve this summation force and y direction and set them equal to 0, and then we can find the x, right? Because we know that the shear force at this point is 0. So let's cut it from here. Okay, so now this is our cut, and whenever you cut a beam, there are always 3 things: the normal force, shear force, and the bending moment. And what matter here is the shear force, actually, because we know that it is equals to 0. So now let's do the summation force in y direction and set them to 0. And 21 positive minus 15 minus the distributed load is actually 8x minus the v equals to 0. We know that v is actually 0, so 21 minus 15 is actually 6, is equal to 8x, and x is going to be 0.75. okay, our x here is 0.75. how about this? This is actually 3 minus 0.75 is actually 2.25. okay, so what is the area of this small triangle? Okay, 0.72 times the height, 6 divided by 2, and it's actually 2.25. okay, how about this? The base is 2.25 times the height is actually minus 18 divided by 2, minus 12.25. okay, And finally, the area of this rectangular is quite easy. Minus 18 times 2 is going to be minus 36. So let's draw our bending diagram now. The integration of this line, you know it, just a slope line, so it's 42, and then also we got 12. 42 plus 12 is what? 42 plus 12, it's actually 54. Okay, this is not a curve, actually. This is just a line, just like this, and then we got a triangle. So because here we are moving from the big to small, so it's fast to low. Okay, so it's actually concave down. So let's make a line here, and it's actually concave down, fast and low. And 54 plus the area is 2.25, here 65.25, and then we move down 20.25, and we reach to what? 63 or 36 actually, and then bam, we reach to 0. And our maximum bending moment is 56.25, and the maximum shear force is 21. Okay, the absolute value. Okay, thank you so much, and I hope you understand and everything is clear. Thank you.